This is 2026 USAJMO Problem 2. So this is Problem 2. There are M foxes and N rabbits sitting in M plus N seats around a circular table. So circular table where all animals are distinguishable. If a fox and a rabbit are sitting next to each other, they may swap positions. For a fixed starting configuration, determine the number of configurations that can be reached by a sequence of swaps. So firstly, we have they're all each animal is distinguishable. So each fox we're gonna have like fox 1, then fox 2, then so on, and then we're gonna get fox sub M. And we're also gonna have rabbit 1, rabbit 2, so on until rabbit sub N. And so this is gonna be all the animals. And so each of these animals is gonna choose a spot around the circular table, and then that's going to be the starting configuration. And from that starting configuration, we want to see how many different starting configurations we can get from just these swaps. So the first thing I'm thinking of, let's just play around with this small example. Let's say we have, instead of a circle, let's say we have a linear table. And let's say, well, we can say without loss of generality that M is greater than or equal to N. Because if there's more rabbits than foxes, we're going to have the same thing. And if there's an equal number, well, that's inside of our case. So we can say that this, without loss of generality, we're going to assume that M is greater than N. There's more foxes than rabbits, because the case is symmetric either way. And so let's just say there's 3 foxes and 2 rabbits. And so we're going to have like 5 dots. 1, 2, 3, 4, 5. And let's just say, for argument's sake, that they're all going to be in right to left order. So like F1, F2, F3, R1, R2. So these are all our animals. And so by making swaps, we can get, let's just make swaps and see what configurations we can get. So we get F1, F2, R1, F3, R2, because I swapped these two. So let's see, I'll swap this again, F1, R1, F2, and I'll swap these two this time, R2, then F3, and so this one I actually did 2 swaps, and so that's there. And so we can keep doing like any number of swaps, but immediately one thing that you realize is that basically the order is going to stay the same. And what I mean by that is F1 is going to happen before F2 or F3. R1 is always going to be before R2. And so the same thing here, F1 is always going to be before F2 or F3. And the reason this is true is because once we get F1, let's say we want to try to move R2 in front of R1. So we'll get F1, then R1, R2, F2, F3. And so once we're here, we can see that rabbit and rabbit cannot swap, and so there's no way for these things to switch around and get R2, R1. And so for this linear, for a case of linear, we have that the order stays the same. But does this hold true for circles? So we'll try constructing a circular table now, or it's going to be a pentagon table since there's 5. So 1, 2, 3, 4, 5. And so let's say there's F1, F2, F3, R1, then R2. And so by doing swaps, is it going to be possible to get R2 in front of R1? And the answer is yes, because there is no clearly defined in front of here. Because let's say we're going to be counting clockwise, or yeah, that's clockwise. Let's say we're counting clockwise. If we start at 1, then 1 is first, but if we start here, then 1 is last. So there's not really a clear order of what's first and what's last. But what we can see here in a circle is that it's not the order that stays the same, but it's sort of like the permutation that stays the same. So speaking of the F's, we can have 1, 2, 3, or we can have 2, 1, or we cannot have 2, 1, 3. We can have 1, 2, 3, or 2, 3, 1, or we could have 3, 1, 2. So these are 3 possible combinations we could have, because they all depend on where we're starting. If we start here, then it's 1, 2, 3. If we start here, then it's 2, 3, then 1. And if we start here, then it's 3, then 1, then 2. And so what we have here is a subset of possible combinations that is possible for the orders of these things. And similarly, the same thing happens with R. And since, R is just 2, there's not really like, it's just 1, 2, and then 2, 1. So there's not really a lot of things to it. But what we see is that with the case of the permutations of the foxes, there's actually a certain group of permutations we can't get. We can't have any swaps. So like 2, 1, 3, we can't have that. Or anything else for that matter. If we can have 2, 1, 3, we can't have 1, 3, 2. Can't have that. And so there's a bunch of these cases. I think there's only one more actually. But we don't really have to find it. So there's 6 total cases, and in 3 of them we can't reach what we want. These are not possible configurations. So now we have a little more information about what this problem is really all about. So we found that basically if we turn this into a circle, what stays the same is the sort of ordering of the foxes, or in the ordering of all the animals with respect to some like counterclockwise. So meaning that we can rotate each of these and they're still going to be the same order, but we cannot make any sort of swaps or anything that changes the relative position of these. So that's what we have. But now we need to determine the number of configurations that can be reached by a sequence of swaps. And what they're asking is usually some formula, so probably some like function in terms of f of m and n, that gives us the number of configurations. So with this knowledge that we have about the circle, let's try to generalize it. So what we can see is when we generalize, we're going to have some circle with, again, without the loss of generality, we're assuming that m is greater than n. And so in this circle, we're going to have some number of m's, and I'll make those solid dots. These can be like white dots. So some number of m's, dot, 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 and then like some number of m's, and like it's just going to look something like this, maybe. That's a white one, that's a white one. And so we see that throughout any sort of swap we could ever make, that these sorts of permutations are going to stay the same up to reordering them. So as long as we don't swap them, as long as it stays in the same order, that's going to be the same. But so how do we formalize that intuition into a formula? So what I'm originally thinking is let's just choose any arbitrary starting position, and using that for any arbitrary starting position, we have an ordering. So for any starting position, we have an ordering, and that ordering is going to stay the same no matter what. So we're going to have maybe like F1, then F2, then F3, and then so on, or we could have like F2, then F1, then F3, and then so on. And these are going to be 2 separate orderings. So it's going to be something like that, and that ordering is going to decide how many possible configurations we could reach. And if we think about it, we can reach pretty much any possible configuration by switches. So like any possible configuration of rabbits and foxes, for example, if we go back here, we could get like F, 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 R, R. We could get any possible configuration of F's, 3 F's, and 2 R's through swaps. We could get like R, R, F, F, F. We could get that. We could get R, F, R, F, F. We could get any of them. So we're not really restricted by what we can achieve, or like, because all the gaps in all these sorts of RF configurations are possible. We're only restricted by the ordering of these. And so let's first try to see, because we're not restricted by this sort of like RF ordering, we can just try to figure out how many RF orderings there are. And so that's going to be pretty easy, because that's just m plus n, choose m, or choose n, doesn't matter here, because they're both going to be the same thing. And so since there's total of m spots, or m plus n spots here, and we want to choose any m of them, or we could choose any n, really doesn't matter. So without the loss of generality, we're going to say it's m. We can choose any m of them and fill them in with f's, and then the rest are going to be filled in with rabbits. That's the other animal, yeah, rabbits. And so we have this many ways that we could choose seats that these rabbits and foxes could sit in. But then once we choose the seats, we want to find for the given starting position, how many other starting positions are there? And so this is where we use our second condition. The second condition is that this sort of like cyclic order stays the same. And so if the cyclic order stays the same, we basically can choose without the loss of generality from these m dots. So let's go back to the pentagon example just to make it a little more clear. And so let's say these shaded dots are going to be reserved for foxes and the non-shaded dots are reserved for rabbits. And so if we've done this math right here, m plus n choose m, we basically have these three dots. But the order, let's say the starting position is like 1, 2, 3, the order is going to stay the same no matter what. So we basically want to find a way to assign the numbers 1, 2, and 3 to these three dots such that when we count this in a counterclockwise order, we're going to get everything that's following here. So either one of these sets is fine when we count in a counterclockwise order. And so the way I'm thinking of doing this is let's just choose a random one of these three ones to be our first one. Because if we choose our first one, that determines where the second one goes, and that determines where the third one goes. And so if we choose, for example, this one, we could choose that one to be the first one. This could be 1, this could be 2, this could be 3. That's one possible way. But we could also switch that to make this 1, this 2, and this 3. And notice that from here, we could get back to the original configuration by making swaps with rabbits. So it's completely possible there. It's just going to be like, we're going to rotate things a little bit. We're going to be making swaps and things like that. And if we go back to the question up here, it says rotations and reflections are considered distinct. So we don't have to worry about, oh, is there like a rotation? Because that's kind of what we're studying. We're studying the rotations. So the way we find that out is we can just multiply by m. And once we multiply by m, all of the rest is automatically determined by the position of that first one. And since there's m spots to choose from, everything else is going to be determined. And if we go back here, for example, m is equal to 3 here, and so we see 3 different possible combinations, each corresponding to which one starts. Is it a 1, is it a 2, or a 3? Or we could talk about it as a position of the 1. So each of the 3 positions of the 1 has a possible configuration we could have. And so we're almost done here with our formula because we have one more thing. Now that we've done the same thing for the foxes, we need to do the same thing for the rabbits. And again, this is probably not the best example since there's only 2, but for the rabbits, we can choose either this one to be the rabbit number 1 or this one to be rabbit number 1. So again, it's going to be just times the number of rabbits since it's going to have to go 1, then 2. So whichever one we choose, it kind of have to go in that order. And so again, another assumption we've made is that like without the loss of generality, we're counting clockwise. But we could have also counted counterclockwise. It would have been the same thing. So we found the formula right here. So the formula is mn times m plus n choose m. And so this will give us the number of possible configurations that can be reached by a sequence of swaps, but it's also including the starting configuration. And we could -1 to not include it, but this just makes it a lot easier. So we'll write m and choose m plus n, or mn times m plus n choose m, including the starting configuration. Because we could technically reach the starting configuration by doing 0 swaps, and that technically counts as a sequence of swaps. So I'm going to include it this way, but if you really wanted to, you could do mn times this -1 and say not including the original. But that's our formula right here. And so we find that this is the answer.